Okay. Hello, everyone. This is hopefully going to be your last high frequency systems lecture. So, what we are going to do, we are going to complete the remaining topics from antennas. And today we are going to cover antenna arrays. So, last time we looked at some antenna fundamentals from practical perspective, what kind of uh, techniques we generally use to build an antennas, what kind of things we look in antennas while developing them. So we looked at fundamentals. We start from Hertzian dipole. We looked at radiation pattern, power density, intensity, beam width, directivity, gain, realized gain. We also looked at radiation resistance, although we do not like to rely too much on radiation resistance. We like to match our load with our sources. That's why we rely more on what input impedance we generally get at the input side of the antenna. Then effective radiating area, radiating efficiency. We know that they are linked with each other. Directivity and gain are linked with each other in terms of efficiency. We also established that 100% efficient antennas are not available in nature. It's just not possible to get a 100% efficient antenna. That's why whenever antenna efficiency is more than say 90% for most important applications, we are okay with it. If for some particular antennas in very harsh environments, if antenna's efficiency is more than 50%, it's still okay. It works for us. A lot of energy gets wasted, but we don't really care about that kind of wastage in some particular applications. For example, if we have implantable antenna, an antenna placed inside human body, want to communicate with an antenna outside human body, then of course it's a harsh environment, it's extremely harsh environment, and antenna radiation efficiency will decay significantly. So we are okay if antenna is operating more than like 30% of its efficiency. We just want it to throw enough energy outside so that we can read what's going on inside human body. And then we looked at from linear antenna, we started we expanded our discussion to Hertzian dipole and half wavelength dipole. We also looked at how we can build a simple dipole, electric dipole using magnetic loop. So magnetic dipole is also another form that we generally use. And today we are going to cover up finite length antennas, polarization and mirror effect, and some additional. I'll just try to give you a bit of taste of propagation, although propagation is not covered in this particular module. But whenever we speak about antennas, we like to speak about propagation as well, because antenna is one thing. It's a converter from currents and voltages to electric and magnetic field, but electric and magnetic field, time varying electric and magnetic field, is going to need to propagate through free space. So there are a lot of considerations about propagation as well. So today we are going to also just very quickly touch upon that, and then we will move towards antenna array topics. So before moving forward, is there any question from last time? So do you have a general understanding how simple antennas work? How simple dipole antennas radiate? Are you comfortable with this understanding of how antennas radiate? Yeah. Okay. Since you already are much familiar with many things, let me ask a few simple questions. So first question, why do we need pair of metals to let our energy flow from point A to point B in our simple electronic systems? What I mean is, if we have a simple battery, we need a pair connected to a load. Okay. Why do we need pair? Or simply, can we do this energy transfer without a pair of metal? So that's a good thing. Okay, imagine I have a very good device here. Science is advanced enough. I have a big ball of metal, okay, and I'm constantly charging it negatively, okay. So there needs to be some positive energy here and negative energy here. So there will always be a flow of energy. So in other way, in other sense, some electrons will jump from here to here. Or let's reverse this polarity just to keep our life simple. So imagine I have a this kind of scenario, okay, in which we have negative charge here, positive charge here, okay. So some energy will flow in single metal strip. So still, when we need a positive and negative, here we have positive and negative. Energy is flowing. Why do we need a pair? That's the right side of thinking. So please go on. Okay, so what you're saying is we need another direction for energy to go back or something like that. Just one thing. If there is a current flow, according to our understanding of electromagnetics, will there be a B here? A current carrying wire will have magnetic field, right? Right? So there will be magnetic field. So electric field is getting electric field is actually there already because of positives and negatives. There is magnetic field because there is instantaneous flow of current. So energy is actually flowing, or is it flowing? Did we establish that we want to let our energy flow from point A to point B, and we want this energy to flow? How energy flows in simple copper pair? In what form? Is it electric energy, magnetic energy, or electromagnetic energy? It's electromagnetic. Okay. What it means is if I have current, there is magnetic field. I'm not sure if it is clear, but there needs to be magnetic field here. Okay. But it's only magnetic field. We need electric field as well, and magnetic field, and electric field, and magnetic field. So in other words, we need a combination of both. Okay. To make sure that we need a combination of both, if we have another pair, and thanks to you, we will have positive and negative pair. And because of this positive and negative pair, we will have flow of electric field, electric field lines. Okay. If we have electric field lines, then because of these electric field lines, we will have magnetic flux density. So something like this in the third dimension. Magnetic flux density will produce an electric field. Electric field density will produce magnetic field. And overall, we will have a flow of energy from one point to the other defined by E cross H. Okay. So we need a pair to make sure that it's electromagnetic energy flowing. It's not only electric, not only magnetic. It's a combination of both electromagnetic energy. Okay, so that's why we need a pair. Of course, this pair can be a simple copper pair. This can be twisted copper pair. This can be a coaxial line. You know about coaxial line? Coaxial line has a conductor in the middle and a shield in the outside. Metallic, you can say a metallic cladding and metallic core. Two things. Simple coaxial line that generally you connect from your antenna and connect from the back of your television just for the television signal reception. Those are okay. So we need both. We need two conductors, and when these two conductors are converted into something that helps electromagnetic energy skip the circuit, that's an antenna. We have seen that antenna has its own properties. It has directivity, it has its gain, it has efficiency, and so on. So coming back to where we left from last time, a simple positive and negative poles of a dipole antenna connected to an alternating voltage source, or we just call it source, can produce fields like this, and these fields skip our device and they propagate in free space using electromagnetic energy flow phenomena that we have already studied. Then we looked at a bunch of definitions, and we were almost here discussing about what kind of radiation we can see if we have half wavelength dipole, if we have full wavelength dipole, and if we have 3 lambda by 2 dipole, and so on. So just to explain what this thing mean, this infinity sign mean. So it's a polar plot. What it means is it has a contour, and this contour represents a value in the direction where we are interested in. So imagine my dipole antenna is sitting like this. Then this contour is saying a high value in this direction. It means there is more directivity in this direction, but this contour is getting smaller and smaller as I am moving towards like theta from 90 to 0. As I'm moving like this, the contour is getting smaller and smaller, and exactly at theta is equal to 0 degree, contour is basically approaching 0. So it means that there is basically no radiation by this dipole in this direction, no radiation in this direction, but there is radiation in these two directions. Plus there is a portion of radiation in these directions. Okay, so this simple radiation pattern, very important thing to understand how antenna is radiating. This is very simplistic one, but we generally like to use more complicated ones. So in your laboratory, for those of you who have already were present in Monday's lab, we have looked at these radiation patterns, and we try to manipulate some of these radiation patterns for our own benefit. Okay, for serving multiple uses from -60 to +60 in azimuth and within a sector, 120-degree sector. We want you to see how many phase states do we need. For those of you who hasn't attended the lab, you will do the same next Monday. Okay, so then we looked at another very important equation that's called Friis free space transmission equation. So Friis free space transmission equation explains something that is very engineering in nature. So what I mean by that, it kind of explains what's outside our control and what's in our control. So this equation is here. It states PR, that is received power PR, received power PR at a distance R from the transmitting antenna is equal to received power at a distance R from transmitting antenna is equal to PT GT GR. PT is power transmitted, so it's power transmitted from here. GT, gain of transmit antenna in the direction. GR, gain of receiver antenna, again in the direction. multiplied by lambda over 4 pi r squared, which is also called path loss. So 4 pi r square over lambda is the path loss. And if I want to make it as I want to say at that it's a loss, then I can see that if I increase my distance, my loss will be more. So distance between transmitter and receiver is generally not in our control. So for example, if you want to communicate from here to HP building and we want to build two antennas to communicate with each other, distance is nothing we can do about. Okay. What we can play around with is lambda. What frequency we select to make sure that our transmitter transmits and receiver at least receives some energy. Okay. So lambda is important. We also have a control on maximum transmit power, PT. What is power equals to in electronic systems? P is equal to P is equal to P is equal to voltage multiplied by current. You know this. Tell me you know this. Thank you. So P is equal to VI. So what it means is the source that I have, voltage source, and how much system is drawing current will define my P. And if I have a good, nice system, then all of this energy will be translated into antenna being radiated. So PT is important. Okay. So gain of transmit antenna is important. We have seen that if I'm using a dipole antenna here, if this is a simple dipole antenna, half wavelength dipole antenna, then it will radiate more in this direction and radiate less in this direction. Basically, no radiation in this direction. But if I want to communicate from here till HB building, then I don't want to waste energy in direction where I don't want. So that's huge wastage of energy in direction, in the opposite direction. Okay. So we don't want this. This is not a good choice of antenna for my this particular application. Okay. So what I need a more directional antenna. So for example, if I have a Yagi Uda antenna, that we are going to study later. If you have a Yagi Uda antenna, then it will be more directional. It will have more directivity towards the radiation and less directivity in the direction where we don't want. Okay. So Yagi Uda antenna is a good choice. So that's why I am doing all this thing, because I know that GT is important. Gain of transmit antenna is important. Similarly, what kind of antenna I need at the receiver, GR is also important. So that GR will also translate into what kind of receive power I will get. Okay. And then receive power is important because receive power will tell me if I can make sense out of the signal that I'm receiving. Okay. And to understand this PR, let me quickly jump towards another concept that is not directly linked with your investigation, but it's useful to know this information. Imagine I am being sent 101010, okay, bits. And these 10s are translated into analog signal being transmitted using any modulation scheme, digital modulation scheme. Let's consider it to be quadrature amplitude modulation or quadrature phase shift keying, QPSK or QAM. Okay. You know about modulation schemes? Have you studied about digital modulation schemes? Just a bit? Not at all? Okay. Forget about what I've just mentioned. I'm sending ones and zeros. Can ones and zeros be sent directly? World is not digital, world is analog. So I need to convert these digital to analog signal. The device is called digital to analog converter, DAC. And we also have an analog to digital converter at the receiver, ADC. Okay. Forget about everything else. Just consider that I have a DAC and ADC pair here. I'm throwing in digital information and it is getting converted into analog information. And that analog information is being thrown by the antenna, being received by the antenna. Okay. So imagine I am looking at frequency spectrum F, and in this frequency spectrum, there is a limitation for me to understand how much, what information is being thrown. So just to give you an example, imagine your friend is sitting in Ashby building and you are here, and you ask your friend, just turn on a light, turn a light on and off, and I will just record that information and I will say 101010. Okay. If your friend is turning on a simple good torch, it's good. But if your friend is turning on an LED there, you cannot see. Okay, because the information that is being propagated through LED from there in form of light will not reach you. It will get attenuated when it is being transmitted through free space, right? So it means that there is a lower limit or called noise floor. Beneath that, you will not be able to understand. So you will just ask your friend, make them two LEDs, and then friend will can make two LEDs and three, four, and five, and then you just will start seeing your signal from basically noise, and then at one point you will see a particular signal coming up your noise floor. It means that okay, you are actually understanding what is being transmitted. If this signal power and noise power is compared, and we call it signal to noise ratio, SNR. In very, very simple terms, it's complicated than that, but in very, very simple terms, if we are talking about a given SNR condition, then we need enough received power PR that is comparable with the SNR requirement of my upcoming system. Okay. So that's why PR is extremely important. Okay. So what this equation that I've shown you is telling us is that received power PR depends on gain of transmit power by the transmitter, gain of transmitter antenna, gain of receiver antenna, and lambda is in our control, but R is not in our control. R will be there. Plus, this is super simplified equation. Okay, so there are many other things. So, for example, between you and your friend, there can be a cloud, and that cloud can just kill your signal. There can be some obstacles. There can be a tree. So many things can happen in free space atmosphere. Okay, so this equation is very idealistic, but it is one of the most important equation in propagation. It's called free space transmission equation, and it also called path loss equation. Path loss equation. Okay, so this is just for your understanding. Of course, we don't want to go any deeper than that. So just to see that in this equation, you might have seen that aperture of the receiver and transmitter antenna is important. So there are multiple methods of improving aperture area. Some methods are you just build a huge dish to capture more energy. You might already have seen dish. So what dish does, it has received a plane wave, a simple plane wave electromagnetic energy, and then it kind of focuses that energy into one point, and from that point we kind of prop the energy out. So similarly, we have multiple antennas doing the same job, so it's basically like increasing the number of LEDs in your aperture. Okay. Similarly, we have like mirror is a similar kind of form, and lens apertures. So what lens does, there is a possibility that energy is flowing through free space as plane wave, and you kind of capture that energy and focus it on a single point P. Okay. Of course, this is again super simplistic, cartoonish kind of diagrams. In real life, this diagram is good enough for one frequency, but our systems have a bandwidth. So we want to build system for a given bandwidth. So it's not as simple as in these cartoons. It's much more complicated than that. But at least this is good enough for understanding concept. Okay, so here's another concept. If we are if our energy is propagating through a particular medium or crossing a boundary, then there are some conditions called boundary conditions that apply. In electromagnetic theory that you have understood so far, we haven't gone deep into boundary conditions, but this is just for your own information. In advanced electromagnetic theory, you will have very clear expressions about what boundary condition means and what boundary condition applies for electric field, magnetic field, tangential electric field, potential magnetic field. For now, it's just a simple expressions just for your understanding that things are not that simple in electromagnetic world. So equation 1 is telling us something. Imagine we have an electric field vector propagating or like going through a boundary, a simple electromagnetic vector going through a boundary. Forgetting about the coordinate system, I can have two projections of that vector. Imagine I have a simple vector propagating through a boundary, electric field vector E, E1, E2. So a vector can be decomposed into two components. Forgetting about coordinate system, it can be decomposed into a parallel and perpendicular component, right? Similarly, consider I have a magnetic flux density vector crossing a boundary. It can be converted into B parallel, B1 parallel, and this is B1 perpendicular. Okay. So how they are connected to each other is shown here in this simple example. So our electric field parallel vector is basically equal to electric field parallel vector in the other boundary. So imagine I have air in one side and this wall concrete on the other side. It's not concrete, is it? No, it's synthetic material. Synthetic material one side, air on the other side. So parallel vector of electric field will have no impact in the boundary. But the perpendicular vector is related to each other with reference to epsilon of each layer. So for example, my epsilon is epsilon naught because it's air in this side, but there is a dielectric or dielectric permittivity for material. So that permittivity has an impact on the perpendicular sector. Okay. Similarly, the perpendicular magnetic flux density component is unchanged when it's crossing a boundary. But parallel one is not unchanged. It has an impact of permeability. So I have to know permeability of free space and then permeability of the material that is propagating through. Okay. So what will happen is E2 will be less than E1 with a unit epsilon 1 over epsilon 2. So if epsilon 1 is say 1 for air and epsilon 2 is 1.2, then of course E2 will be less. So it means that there is an additional propagation loss when electric field vectors change its boundaries or go from one boundary to the other and so on. This is very useful information. So I think I've already given you the solution of this example. I was not supposed to do that, but anyways. So an AM radio station have frequency 535 to 1605 kilohertz. This particular tower is at 700 kilohertz. How tower length relate to AM signal? So it's a very simple example to showcase uh, a, a tower that's in USA, and frequency of operation is 710 is per 3 hertz, and wavelength will be 429 meters. So if we want to build a lambda by 4 monopole antenna to do job of broadcasting electromagnetic energy in free space, then we can do that using this tower having lambda by 4 length that is almost 107 meters. So this tower need to be 107-meter long, need to have a source connected to it, and that source needs to be operating at 710 per 3 hertz, and then this tower will radiate energy in free space. And any receiver that can cache this signal will be able to cache this signal. So this is just to showcase the relationship, a very clear relationship between length of antennas, or actually dimension of antennas, and frequency of their operation. Okay. So another very important concept is polarization. So just to give you a simple understanding, what does it mean? We have actually understood in greater detail that how a simple dipole radiates. Okay. In this dipole, in which direction will I have the change of charges? In this direction. So plus and negative, 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 right? So what it means is my electric field will be produced like this. Electric field vector will be produced like this. Okay. So now imagine I have one dipole sitting like this, and my receiver dipole is tilted 90 degrees. Will it receive anything? It shouldn't receive anything. So if I have a dipole sitting like this, then it will not receive anything because the electric field propagation is along the other dimension. So electric field is oscillating with respect to time in this direction, but my dipole is in this direction, so it will not receive anything. Okay, so this concept is generally translated as simple polarization. So what I've just shown you is two linearly polarized antennas, and they are kind of linked with each other perpendicularly, so that's why they are not going to receive any energy. So we have two polarization components. One is horizontal, two sort of polarizations. One is horizontal polarization, one is vertical polarization. This is journal for our journal antennas. So if you are building a simple dipole antenna to receive television signal, and that antenna is like this with multiple knobs, then it means that it is receiving a horizontal polarization component only. Okay, but now our devices, our mobile phones, these sort of devices, consumer electronic antennas have multiple polarization components, so they are capable of receiving energy in any polarization basically. Okay, so horizontal polarization component, vertical polarization component. So if we recall wave equation, where we only have EY component, then we can say that if electric field is propagating or electric field is time varying and space varying only in Y axis, then we need antenna to be along Y axis as well to capture that energy. If it is not in Y, then it's not going to receive anything. So in real life, there is a possibility that I don't have this kind of antenna receiving nothing, but I have another, you can say, component of this antenna, something like this, that is only this portion is receiving energy in the other polarization component as well. Okay, so if you open up your consumer electronics, your antennas will be will be a little bit weird in shape. So for example, if you open some old phones, then the antenna there will look something like this, shot from here and there. Okay, so it will be able to collect vertical polarization and horizontal polarization, but of course that polarization component will be very weak. The other polarization components will be very weak. So these sort of antennas are also available. Similarly, if you look at this new Apple Watch thingy, then I'm not 100% sure about it, but I think something like this. So it will have a capacity of receiving vertical polarization and horizontal polarization as well. Okay. So similarly, a GPS receiver like to use circular polarization to receive signal, like receive very good signal strength. We will look at circular polarization. Okay. So vertical polarization, horizontal polarization, is it clear enough? Yeah. Okay. So circular polarization is when the vector, electric field vector, is propagating through free space, but it is changing its electric field vector. Okay, so electric field vector, if it an electric field vector is propagating in along EY, but is not staying along EY, is kind of changing and going to EX as well, and then EY and EX and EY, then it is kind of considered as circularly polarized electromagnetic wave. So CP is an idealistic condition. So it can either go clockwise or anti-clockwise. Okay, so clockwise and anti-clockwise. So it depends on what kind of application you're interested in. Some applications like to use circular polarization signal because they don't want energy to just get not to be received by anything. So if a CP signal is thrown and you have a linear polarized antenna, then you will receive at least something. At least half of the energy you will be able to receive in ideal conditions. So for example, if there is a circular polarization signal coming from GPS satellite and I have a linearly polarized antenna sitting here, it will receive half of the energy that it should have received here if it was a pure circular polarized antenna. Okay. So in your module notes, so it's something like this. If we build an aperture and looked at a circularly polarized electromagnetic signal, then its electric field component along x-axis and along y-axis will be rotating in one wavelength. So in one wavelength, when one wavelength will be propagating through our aperture, then electric field vector will complete its one circle from 0 to 2 pi. Okay, so this is a simple demonstration of circular polarized antenna. I have provided a few videos around circular polarization wave in your module support material. It was from NASA. It's open access video, so you're free to use them and you're free to use them for your own understanding. Okay, elliptical polarization. So here's a concept. In an ideal world, a pure circular polarization is possible. So what it means is an electric field changing its orientation as one wavelength is completing. is possible. But in real life, pure circular polarization at one particular frequency is okay, but for a wider bandwidth is not possible. So what will happen in reality is one vector of electric field in one axis will be larger than the electric field vector in the other field. So what it will manifest? It will manifest into a polarization that is somewhere in between pure circular polarization and pure linear polarization. Okay, so what I mean by that is, imagine I have this linearly polarized antenna and a simple circularly polarized antenna here, and another with a 90-degree of phase shift. Phase difference delta phi is 90-degree. Sorry, phi is what you already know, so let's make it a capital phi, delta phi. Okay, so this is producing a circularly polarized electric field vector. Okay, if we look from this direction, then this vector will look something like a circle, pure circle. If we look at from this direction, for this one, our electric field vector will look something like this, propagating up and down and up and down and up and down. And here it will be rotating along this circle. Okay, but in reality, we will get something that is in the middle. So something like this, an ellipse, where electric field is more in one direction, in one particular point in time when wavelength is moving across our entire aperture, and for some points it will be less. So our ideal circular polarized condition is not possible for all frequency bands, so it will be elliptical polarization. And if it is too elliptical, it means that if it is too elliptical like this, long vector here, short vector here, so then we can say that okay, it is almost a linear polarization. It is almost linearly polarized. So ideally, this is what we generally get. In practical systems, we get a good elliptical polarization that is close to circular polarization. We consider it circular polarization, circularly polarized. Or we get something like this, which is close to linear polarization. Okay, so this is more, you can say, plausible in our practical scenarios. So here's another thing. If you are an extremely good engineer and you build a circular polarized signal and then throw it through free space, then during its propagation, it can actually face depolarization because of its because a signal is propagating through this material, through walls, through trees, through land, and then just hitting land and getting reflected back. So these kind of things are called depolarization, and they are actually there. So we have to be considerate about them. So in an ideal world, what we need to do, we need to have a linearly polarized vector and a horizontally polarized vector, and we kind of build our antenna system such a way that any polarization vector that is being propagated through free space is able to be received. Okay, so this is kind of you can say one consideration. Of course, I'm not going to ask you to build something like this. It's just for your understanding. Okay, and this there's another animation just showcasing how electric field vector that is shown in green is changing as wave is propagating through free space, and this red and blue are its components in E and Y, in X and Y. Sorry. Okay, so this is a pure circular polarization system. So again, the same concept that I have mentioned here is shown here. It is a good a good, you can say, approximation for us to understand how circularly polarized an antenna is called axial ratio. So axial ratio is basically ratio of two components of electric field. So if you look at the diagram on the top side, now we are considering a simple Cartesian coordinate system in which we have an x-axis, we have y-axis. Electric field vector is shown in red, and it has EY component and EX component. Okay, so if there is this phase difference between these two is 90 degrees, then this psi, sorry, 45 degrees, then we can understand that it's basically an elliptical polarization. So now in the first diagram, what I have just mentioned, the board is kind of given in an animation side in which you have a linearly polarized, linear polarization being explained. On one side, we have circular polarized, right-hand circular polarization, or you can say clockwise circular polarization. And then third is elliptical polarization. So our axial ratio can go all the way from 1 to infinity, or in dB scale from 0 dB to infinity dB. And we like to say that if axial ratio is less than 3 dB, it means it's enough circular polarization for our application. Okay, so we don't go and try to achieve ideal conditions. Okay, any questions? No. Okay, so a bunch of very final comments that are part of your module is mirror effect. So mirror effect is something like this. Imagine if I have half wavelength dipole like this one, same is given there, and we kind of, in time, we are varying its positive charge, and then we are shifting it from positive charge to negative charge. Okay. If we have a ground plane on this top side of this dipole antenna, then because of an effect called mirror effect, physically a hypothetical pole will exist in the negative side, and it will kind of give us an effect that it's a full dipole. Although it's a simple monopole, it will act as it's a dipole. Okay, so what will happen if I have a mirror, there will be a virtual element. So that's why you see there are those long towers like the one in Davos can radiate because they have a ground, and that ground has moisture in it, so it acts like a metallic ground plate. Okay, so that's why it will have a mirror effect, and because of that mirror effect, it will actually work as a dipole antenna. If there was no mirror effect, then having nothing here would have created nothing, but it kind of creates a virtual negative side. Of course, this phenomena is not an ideal phenomena. The antenna, a monopole antenna with a ground plane, cannot be as good as a simple dipole antenna. It will not have exactly same radiation performance, but it will still work. Okay, so that's why we generally like to use this mirror effect for our own benefit. So it's similar kind of thing that if you have a PCB, printed circuit board, and printed circuit board has, you can say, metal in it, then we can use that metal to actually achieve mirror effects and make our antennas radiate. So if we have a simple monopole here fed from here, then because of this ground plane, we will get a mirror effect, and we can actually let our device radiate. What's happening? Okay, please ignore this noise. So here are a few effects that are that I wanted to showcase. It's not a part of your final examination. It's about propagation, but I will come to it after our antenna summary. So as we have seen by start, we have looked at all these different topics, and we have just covered polarization and mirror effect as well. Okay, so I won't be asking you to derive a mirror effect expression. I will just ask you to describe the concept in the final examination. So don't worry too much about these things. Okay. So any questions from antennas? Are they clear enough? Yeah. Okay. So our next and final topic for semester 1 is antenna arrays. So what we will cover? We will cover antenna array fundamentals, two element array, n element array, uniform amplitude and spacing, non-uniform amplitude and spacing, and 2D antenna arrays. And afterwards, we are going to see how this, whatever we have studied, relates very nicely with the communication, with general communication structures or systems, and specifically wireless communication systems. Okay. So let me first describe philosophy of antennas. Imagine I have a simple antenna placed here, and it has a directivity pattern like this. It means it is radiating good at a given gain G in this direction. And because of this transmit power that is available here, it can reach till 10 kilometers. Okay. And after 10 kilometers, its energy will go below noise floor, and basically any receiver after 10 kilometers will receive nothing. Okay. Now consider if my receiver antenna is at 15 kilometers. Put on your thinking cap. What can we do? What can we do? Increase? That's to increase the power PT. So imagine my previous PT was 10 W. My new PT is 15 watt. Okay. Then what will happen? My energy will be enough to get here. Now imagine my antenna cannot draw this much energy from my source. So it is already at its maximum power limit. Or the power amplifier that I have, a power amplifier, has a maximum gain of say 10 dB, and that's the maximum energy it can actually give me. So it's very power amplifier specific kind of thing. If I have this scenario, what else can I do? Increase the frequency or decrease the frequency? So wavelength, if my wavelength is increased, then same energy can be propagated further. And increasing frequency means decreasing, increasing lambda means decreasing frequency. Because C is equal to F lambda and lambda is equal to C over F. So basically lambda is inversely proportional to F. Okay. So if I increase my wavelength to propagate my signal farther, then my frequency has to be decreased. That's another way. Okay, so frequency is in our control. Perfect. PT is on control. What else is in our control? Imagine gain of receiver antenna is constant. GR is not changed. GR cannot be changed. What else we can do? Increase GT. So it's a gain. So gain of transmitted antenna can be increased, GT. Okay. How do you think can transmit antenna gain can be increased? Imagine I have a simple dipole antenna. How can I increase its gain? Improving the directivity. Okay, that's an excellent point. So directivity needs to be increased, which will increase it equivalent to increasing gain. And how can we do that for a simple dipole antenna? If I have a simple dipole antenna, how can I increase selectivity? Okay, so one reflected plate. What we have learned from reflected plate, if there is a ground plane, what will happen? Mirror effect. If I have a reflected plate on the back side of a dipole antenna, then what it will create? It will create a virtual dipole antenna. So it means that I have created two dipole antennas now. That's an array of antennas. Now there are two elements. So these two elements, if this distance is carefully manifested, then this previous antenna was radiating like this. Because of this mirror effect, it will radiate like this. So my gain of GT has increased by this mirror effect. Okay, so it's an excellent solution. So that's why you might have seen reflectors behind antennas. And it will do another thing. It will reduce my energy from wasting in the side where I don't want. So previous back lobe was this much, new back lobe is this. So this is old, this is new. Excellent solution. What other solution do you think of? Any other solution? Just forget about this antenna, throw it away. Get a very high gain antenna here. Okay. So I can use a simple horn antenna here that has more gain. So gain of horn antenna, GT, is more. So it can do this job for me. Right? There's another simpler way, but it requires more hardware, more things. That simpler way is to add another dipole antenna here. Here. This is also a kind of virtual array. This is an actual array. This is virtual array. This is an actual array. What it will do? It will also radiate in a similar fashion along this direction with a gain GT. So the total gain that I will get is previous GT and the new GT, or in dB scale, addition of two transmitted antenna gains. So I can double the gain by adding another antenna here. Okay. I can do the same by adding antenna here as well, GT. So now I can increase the power 3 times. So what this will do, if I just have another antenna here, then I can increase energy from here to here, and then eventually to here. And then GR will be receiving antenna. It's a similar kind of technique that I mentioned before, if your friend is increasing the number of LEDs in an aperture, then eventually you will see the light. Eventually. Okay. So it's a similar kind of concept. The set of solutions that you have mentioned are very good. So they are very good solutions. And they actually, all of them, we like to use all of them. Okay. So it's power. We want to couple maximum energy from our source to our antenna. We want to do perfect impedance matching. If you want to study more about it, there is another module in your level 3 high frequency systems techniques. It kind of go a little bit deeper than what you're doing now. Also, we can increase the number of transmit antenna gain, increase transmit antenna gain, increase the receiver antenna gain, and both can be done. Transmit antenna gain, receiver antenna can be done by just removing very bad gain antennas and adding some very good gain antennas, or gain antennas that we actually like. Okay. And there is another method that's called antenna arrays. So we can actually increase the number of antennas to do the job for us, or kind of help each other to throw energy in the direction. But there are consequences of using antennas, using multiple antennas. There are significant consequences. And if you're not considerate about those consequences, then we can easily mess up our even previous simple antenna, single antenna transmitter, single antenna receiver system. Okay, so we have to be very, very careful about what we do. So that constitute us to study more about antenna array theory. So just connecting our discussion from electromagnetic theory, we have seen according to Coulomb's law, if we have a charge in free space, and I am considering a point P here, will that charge has an impact on this point? It will exert a force on another charge if it is placed here. If there's no charge present, then it will have electric field vector, right? We have also seen if I move this one charge to that point, then there will be another electric field, and these two electric field will be combined. There will be vector summation, and I will have a resultant electric field, right? Was this concept clear? Now we are kind of expanding that concept. So now imagine I have bunch of charges on one dipole producing and multiple electric fields and a total resultant electric field E here. Now imagine I have another element here, another antenna here, and it is producing bunch of electric fields and then my total electric field E. I have E1, I have E2, two electric fields. Then what will happen at this point? My total electric field will be a vector summation of these two. Okay. So for example, if I have electric field vector 1 by first antenna, electric field vector 2 by second antenna, then the total resultant will be basically ER squared is equal to E1 squared plus E2 squared plus 2 E1 E2 cos psi. And psi is the phase difference between these two antenna elements. Okay, if they are in the same phase, then there is a fair chance, and if they're in same orientation, then there is fair chance that I can increase their electric field vector by 2. So imagine I have electric field vector 1 in this direction, electric field vector 2 in this direction, E1, E2. Then if I have a combination of these two, then it can go to E1 plus E2 is equal to resultant. So double the total strength, or we can call it intensity of electric field. Okay. So if I do a little bit of maths, then I will end up with this term 2e square cos square psi by 2. And if I have this kind of scenario in which I have two antennas here, and I'm radiating in the both side direction, then it's okay. Everything is good. But what will happen if my direction of propagation is not perpendicular to the way antennas are placed? Let me explain what I mean by that. So are you comfortable with this concept? Yeah. Okay. Now, in the previous example, we have two antennas like this, and our receiver antenna is here. So it means that energy will kind of double in this direction. Okay. What if we move this antenna from here to here? What will happen now? What will happen now? Now my vector sum will not be as simple as I was mentioning before. It will get a little bit complicated than that. So if I have the distance between my transmit antenna and my receive antennas is too much, then the two lines that will connect my transmit antenna to a receive antenna will almost be parallel. So for example, if this dipole is here, these two lines are not parallel. But if this dipole was like far, far away in this direction, then these two lines would have been parallel. Okay. If these two lines are parallel, then here I will have a right angle triangle, something like this. And if I have a right angle triangle there, then I can write an expression about resultant electric field. So expression goes something like this. Simple trigonometric identity. AC, A is place of first antenna, B is place of second antenna, and C is a point where their both path lengths are same. So my AC is equal to D cos theta. D is the distance between two antennas. Okay. If I have D cos theta, it's basically in degrees. If I want to convert it into radian, then 2 pi by lambda is multiplied by D cos theta. And now I have AC is in radian as 2 pi D over lambda. So my resultant ER will be E electric field under root 2 cos pi D over lambda cos theta. So this expression, I'm kind of connecting this expression with the expression in the last slide, and my resultant ER will be a cosine function within a cosine function. So it's a bit it it looks a bit weird. So have you ever seen this before? Yeah. Have you ever seen this before? Yeah. So a cosine function resultant is an angle of another cosine function. Okay, so for example, if my theta is 90, what will be my cos? Cos 90 is 0. So I will get 0 here. And what is cos 0? 1. So resultant of this will be 1. It is a bit weird. So when we will plot the graph, then you will see what I'm talking about. Similarly, if I have cos theta is 180, what is cos 180? What is cos 180? What is cos 180? 0. What is cos 0? What is cos 180? What is cosine of 180? Pull out your calculators. What is cosine 180 in degrees? -1. So, okay, -1. Does cosine -1 make sense? cosine of -1. Does this make sense? It cannot be a degree. So this -1 answer need to be in radian. So what I need this theta to first be converted into radian scales from 0 to 2 pi, and then do this conversion in radian. It will make my life easier. Okay, so if I have radian conversion in cosine of a cosine, then my life will be easy. And if we plot this particular expression, then the first side electric field under root 2 is a constant thing. The next side is a function. If I take this function separately, cos pi d over lambda multiplied by cos theta as within the zone of another cosine function, then this particular factor is called array factor. Okay. And array factor is an extremely useful thing for array designers. So it kind of explains how antenna radiation patterns will look like if I have placed it in this form. So in your lab assignment, you actually build array factors basically. So you have these dots as antennas, isotropic antennas, and then you actually saw what kind of radiation pattern they are giving. Okay, so if I have simple two antenna elements placed at half wavelength distance, then their radiation will look something like this. So maximum direction is under root 2 in these two directions. And if I have these two antennas placed or point sources placed at a distance of lambda, then my radiation pattern or solution of this array factor equation will be something like this. Okay, so now it has 4 nulls and then 2 maximum direction of radiation. This is extremely useful, but of course you will not understand it right away from here, from this. So if we want to have maximum radiation directivity or maximum directivity direction a little bit different as compared to what we have seen here. Okay, just one thing. I think I haven't given you guys break, so please have a break till we will meet again at 12:27. So another very useful thing that we can do is tilt the beam or steer the maximum directivity direction towards where we want it to be. So for example, now let's look at another equation which also involve a phase shift in addition to my pi d over lambda square over lambda naught cos theta expression. So in the expression and in the last slide, we had cos pi d over lambda naught cos theta. But if we add a phase shift here called alpha over 2, just naming it this phase shift, then we can actually tilt our maximum directivity the direction. So let's look closely at these three plots. So how many of you are comfortable with the word array factor? We have seen array factor in the last slide. You know what array factor? Yes? Okay. How many of you have seen a dipole antenna radiation patterns before? You've seen them? So a dipole antenna radiation pattern is something like this. So if I have a dipole antenna here, it will radiate more in this direction, radiate nothing in these two directions, so it will have radiation pattern something like this. Okay, so this is maximum 1, this is minimum 0. This is a simple dipole radiation pattern. Okay, the first one is the radiation pattern of array factor. If I just plot array factor from my previous slide, if I just plot this array factor of lambda by 2, then this is what I will get. If I have dipole radiation pattern, then what happens in real life as a combination array factor is purely mathematical thing. It doesn't have any meaning in real life. My dipole radiation pattern has a meaning. So my total array patterns will be array factor multiplied by dipole's radiation pattern. So if I just multiply these two radiation patterns or multiply the values of these two at every point, then I will eventually get a radiation pattern, a combined radiation pattern, something like this. Okay, so mathematical expression for these are a little bit complex. I'm not going to ask you about them, just for your own information. So if you want to multiply these two, then you will get this resultant. Or mathematically, if you multiply these two, you will get this resultant. Okay, make sense? So what have we learned? If we know about array factor, mathematical expression, simple mathematical expression, if we have any antenna with any given radiation pattern, we can multiply these two to find an array radiation pattern, full array radiation pattern. And this is we generally do. So we have a bunch of examples of array. And if we can expand this kind of concept from 2 elements to n elements. So in 2 elements, we had 2 vectors. In n elements, we will have n vectors. N vectors means if we have one electric field vector by first antenna, second electric field vector by second antenna, third electric field vector by third antenna, and so on, then what we can do, we can have a resultant electric field vector that is a combination of all the antenna electric fields. That can be ER, a resultant ER. Okay, and their phase difference between 2 elements can be 0, it can be another value. If it is 0, then what it means is I'm exciting all these antennas by same signal that has same frequency. But if there has a phase difference, then it means that I'm exciting my first element by 0-degree phase, same frequency signal, 0-degree phase, and then same frequency signal, but a 5 frequency difference, and then 2 phi, and then 3 phi. Okay, so it can be if I have multiple antennas, I'm exciting them equally, and at the same time, then they will all radiate equally in this direction. But if I excite this one first, this one second, this one third, this one fourth, then this wave will start propagating already, and then this wave will catch up, and then this wave will catch up. and then the maximum directivity radiation will be something like in this direction. Okay, this is what phase shift does. So if I just combine this, all the things that I have developed so far, I will end up with this final expression of array factor, sorry, for antenna radiation pattern, which is basically a resultant vector ER is equal to E over under root n multiplied by sine n pi by lambda d cos theta over sine pi by lambda d cos theta. So the expression on the top has n in it. So if n is 1, then these two terms will cancel out. There's no array factor, basically. If n is 2, then of course these two expressions will be different. N is 3 and 4 and 5 and 6, then we can actually expand this expression further. And then eventually we can end up with the final radiation pattern of the antennas. Of course, our exercise, during our lab exercise, we will do something like this. So this slide actually explains the consequences. Okay. So in this diagram, if our n is 2 in this array factor expression, if our n is 2, then my resultant vector will look something like this. The resultant plot of this expression will look something like this. What it is telling us is it has array factor is 2. It means it is increasing the energy by 2 times, but it has 1 null. That's good enough for me, no problem. But if I increase n from 2 to 3, then I will have thrice the power, but the area which I'm going to capture using this phi is getting less. So it can go n to 5 is like maximum here is 5. Maximum here you can see is 5, but I'm getting multiple nulls. And here maximum can be 10, but I'm getting too many nulls. So it means that increasing the number of antenna elements will actually throw more energy in one direction, but it will make our you can say useful area of directivity as less as it can be. But it's not a bad thing for us. We're just plotting the antenna, this array factor in the polar plot as well. It's the same kind of concept. It's of course it's given in your lecture notes. This kind of thing that we want to do using this phase shift is helpful. So for example, if we have many antennas or n is huge, say n is 10, and I have very less directivity beam, but I can move this beam up and down using phase, using the phase of this antenna, this array. Okay. So now let's look at the same example. Previously, my dipole antennas were placed vertically like this. Now, let me just place those dipole antennas in the other axis, say y-axis, and x-axis. And this kind of arrangement is very common in our radar application. So if you look at this radar, you might have seen this radar before. It has another antenna array on top, and that antenna array has multiple dipoles sitting like this in an arrangement that is shown here in this diagram along x-axis. And if you want to look at the array factors, AF, it's same expression, sine n pi by lambda naught d cos theta, and same as before. And if I plot this array factor expression, then I will get something like this in y-axis, in zy plane, and that in xy plane. So I have more number of nulls in my xy plane, but only 2 nulls, because if I look from here, if I look from x-axis here, then I will only see one antenna and the other antenna hidden on the backside. So there will be no difference in the radiation pattern in this axis. But if I look at from the front side or from the top side, then it will have multiple nulls and its directivity will be more, but there will be more nulls. So it only can capture, it can only cover this particular area. These nulls are okay, but they can serve some uses, but it's too risky for building an antenna system that has these many nulls. So it is not good enough to capture anywhere along x-axis, and y-axis, only good enough along y-axis only, not along these sectors from top and bottom. Okay, so that's why these antennas uh, can actually capture energy in a very narrow band, narrow beam width, and we use mechanical means to actually just move this array in 180-degree rotation. So we mechanically rotate our radars. Otherwise, there's no point. Otherwise, it will basically not capture a lot of energy that we need from other directions. So this is an example of bore sight array. Bore sight is, if I have an aperture here, this is bore sight. So for screen, bore sight is this direction. For us, our two eyes, bore sight is this direction. We can also build end fire antennas. And fire antennas are, one example is something like this. It's basically a simple television antenna. So what it does, it has one dipole at the front, and then we have multiple parasitic dipoles, and these dipoles are lambda by 4 from each other. So what it helps in, it kind of excites each antenna at a given phase difference, and that phase difference is such that along x-axis you will get constructive interference, and along all other directions you will get something that is not very useful. Okay, so these kind of antennas are called end fire antennas, and their radiation pattern will look something like this. So if I have z x-axis, and if I plot zx, then it will have maximum directivity in this direction, and then a lot of nulls and side lobes on the back side. Similarly, we have in the other axis, but this zy plane is basically useless for us because their radiation is not very prominent. Okay, so now if we want to expand from these linear antennas to more, you can say, useful antennas, then there's another formation that's called two-dimensional antennas. It can be of any shape. It can be a rectangular, circular, multiple shapes exist in multiple different applications. So for example, here you can see it's a base station antenna for 5G base station antennas. It is, I think, now deployed in many different areas. So this each element is single antenna. It has a weird shape. You don't need to worry too much about it. Just consider them to be dipoles. So they are kind of cross-shaped dipoles excited separately. So this is produced electric field along one dimension. This is produced horizontal electric field and vertical electric field. Okay, so this is an actual antenna that actual base station array that kind of serves your phone. And this is not single antenna, it's an array of antenna, and the array formation is something like that. So there are multiple antennas in x-axis, multiple antennas in y-axis. So ideally it's called uniform rectangular array. Why we use word uniform? Because the gap between these antennas is uniform. Rectangular because it has rectangular shape. Array because there are a bunch of antenna elements. Same antenna theory applies. Everything else remains the same. And then we can have multiple shapes of antennas. This we can have. First formation is that we have seen in the previous slide was uniform rectangular array. This formation is circular array, planar circular array. Then we have circular array, actual arrays in circular formation. Then we can have those antennas. They have multiple names. Some people call them thinned antenna arrays. Some people call them virtual antenna arrays, in which there are some virtual elements and they don't exist actually, but they exist mathematically. So, and antenna array aperture have like huge, enormous number of applications. So we can go from extremely large antenna arrays. For example, here we have VLA. It's used for space astronomy. This is very specific for space astronomy. And They are specific not for communication, but they are similar arrays available for communication as well. So not this particular diagram, but there are multiple other antenna arrays of similar nature that kind of receive very, 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 very small signals from far, far, far away. Okay. So I think there are multiple satellites that we have thrown and they are now far, far away from Earth. They throw signal out, and then we need these kind of huge antenna arrays to receive that signal. Signal is extremely weak. So we have NevoAm integrated radar system, and this radar system has same antenna theory. There's nothing super complicated here. It's basically a bunch of antennas, and those bunch of antennas are placed in a formation that can actually give us a clear understanding of what kind of frequency they will be working on. We can actually figure that out just by looking at this antenna array. And these are used for multiple purposes, for radars, for command and control, like many other military uses. Similarly, we have recently developed multiple satellite transceivers. These are also antenna arrays. So what's in this diagram? These small little areas with shape like this are called patch antenna, patch antennas, and there are a bunch of these, and all of these are connected through bunch of transmission lines, and these transmission lines are basically metallic stripes with a given a width, and each width of these transmission line will define their own input impedance, and that's why it looks a little bit complicated. But if you just look at the theoretical concept, it's pretty reasonable. All antennas are, you can say, equidistant on the top side and equidistant on the bottom side, so they can be considered as 3 cross n rectangular array and an array of arrays. So they're kind of array of arrays. So they can be like their radiation performance can be calculated directly by using the same kind of expressions that we used before. So something I mentioned before, if we have same array factor equation or resultant electric field equation, and we have this alpha by 2, then by changing this alpha by 2, we can actually change the maximum directivity radiation from both side to any other direction, in positive side and negative sides. Okay, so this is what we generally use in our very sophisticated designs now. So there are a few such examples given in this particular um, uh, very helpful slide set. I will explain this more during our lab. So this is basically a simple demonstration of what happens if you have multiple phase. So we can just look at an example of simple water waves. So if we throw a bunch of stones at the same time in water, then waves will propagate in water, and they will be equal phase along these two directions, and they will kind of cancel out each other in these two directions. But if we throw these pebbles at a given phase or phase difference, or means one after other with a slight phase difference, then their constructive interference direction can be changed. Okay, so this is what we do when we excite antennas with a given phase difference, and that phase difference is written here in this equation by this alpha by 2 plus minus alpha by 2. So I can change this alpha by 2. Now these, because of these advancements, we have like gone from very um not super sophisticated systems to very sophisticated systems. So for example, in the previous version of this aircraft, a radar, we have a mechanical radar. So in this radar, we have an antenna array. That antenna array is very good, but the radar needs to move mechanically, need to be moved mechanically like this. So a person need to go like this to actually detect the RCS or radar cross section from the enemy or friend or foe thing. So in the previous version, it was like this, but in the advanced version, we have fully functional phased array radar. So it basically applies the theoretical concept that we have just studied of phased array. So phased array means we have full control of alpha by 2 in a hardware setting. So if we have full control of alpha by 2, then we can actually tilt beam in any direction we want, and we can do it in real time, so that this aircraft will definitely have very high speed. So previous version was doing something like that mechanically, just to identify a friend or foe. But this new system does something like this. Okay, so there's a huge, you can say, technological advancement because of this array advancement. So that's why now, since systems are becoming better and better and better, so we need all these we need all this understanding to be able to develop such concepts. So what we have covered in array, antenna array fundamentals, two element, n element arrays, what will happen in electric field vector, uniform amplitude and spacing, non-uniform amplitude and spacing, and 2D antenna arrays. So that's it, guys, for your semester 1. That's it. You don't need to study anymore. So just to give you a bit of canvas QB. Okay. So I will speak about your final examinations. So please be with me. Okay. If you look at your module notes and everything, then you can see there are some tutorial questions and solutions, specimen question and solutions. So first version is gapped. So this is for your own practice, so that you can do everything yourself. And the second one is filled. Filled means it has everything that you need, and it's called a solved solution. So these are only for numerical questions, and only few numerical questions, not all. Okay. So these are just for few numerical questions that may be covered in your final examination. Other than that, everything that I'm going to ask is in your lecture notes. Okay. So if you have understood this, what we have covered here, if you have a reasonable idea about what we have covered, and you can give me like kind of understanding, then you should do good. I am going to ask you to derive only whenever we have driven from fundamental principles in our during our lectures. I'm not going to ask you to derive everything from scratch, because you're not expected to do that. But you need to know what's happening in a particular equation. So for example, if I give you a pointing vector, you should know what is pointing vector and what is each expression means. So what is mu naught? What is eta? What is E? What is B? How E and B are related to each other, and so on. Okay. So similarly, from your antenna arrays and antenna arrays and antenna concepts, you need to know what is free space transmission equation mean actually. What you can do if you are being tasked to develop a system that can throw energy from point A to point B with a distance r is equal to this, then what can be done? Okay. So in your coursework, you have one question that is linked with your lab. So when you do your lab, when you complete your lab, it is a good practice to just think that this information will be useful in your coursework. So if you return me a good coursework, that is for 10 marks, if you take 9 out of 10 marks, and if you give me a good lab assignment, so majority of you will get 4 or 5 marks, then 4 or 5 plus 10, so you will already get, say, 13 to 14 marks from your part A, and 35% is your total final examination marks. Okay. So out of 50 from semester 1, passing marks are 20%, right? So you're already sitting at 13 to 14 from part A. So you just need like 6 marks in your final exam. So please don't tell me you don't take 6 marks in your final exam if you give me good coursework and good lab. Okay, so you just need 6 marks to pass if you get 13 to 14 marks in your final exams, in your coursework and lab. Okay, do good lab, give me a good coursework, get to this 13 to 14 mark level. If you're at 13 to 14 level in your final exam, you just need 6. Of course, I don't want to give me 6 out of 35. I want you to be at 30 level, at least at 30 level, because this module is, it looks complicated, but when you will start studying, you will see that it's super easy. Not that easy, but yeah. Yes. Examination will be in May. Yeah, yeah. You will get the timetable. Yes. There will be no class next week. Yes, there will be no class next week. Yeah. Yes. Now, those gaps will stay there. But if you have a specific reason, that you have a solid reason, and you want to ask me to give you gap notes, and you kind of define that reason in an email nicely, then of course after going through a procedure, I can share that information with you, but not like, ideally speaking, those gap notes didn't had too much gaps. Like you can just sit down with your friend, just give him a lunch or something, and then just write down everything that they have written. Okay, so I have provided you lecture notes, I have provided you everything, you just had a pen to fill them. Of course, some of the information might be missed, so that's why it will excite you to do those group studies. You can just have this places booked, and then yeah. Two separate. Okay, so about final examination, I think this information is already available, but I will just go through that information very quickly. So, guys, we just have 5 more minutes. So, in 5 more minutes, the information that I'm going to share will be very, very useful. So, please be with me. Huh. So, okay. So, that's your assessment, total assessment. So, very quickly, you had part A and part B. So, examination is 75%, and coursework is 10% from part A and 5% from part B. 10% from part A, and there is one lab of 5% from part A. Okay, so just forget about everything. Look at laboratory. 5% is lab 1 from semester 1. Okay, there will be only one lab in semester 1. I've already given you a lab assignment, and I have taken back that lab assignment, field lab assignment. So you will get 5% or 4% or 3%, depending upon what you have given me. Okay, out of that. Then there'll be 2 more labs in your semester 2. Okay, Stelinos is going to handle those 2 labs. Okay, I think they will be same lab demonstrator, but Stelinos will take care of these 2 labs. There is no coursework in second semester. There's only one coursework in semester 1. I've already given you coursework. I hope you have already completed that, and you will not copy each other's coursework, because that's a crime. Don't copy each other's coursework. If you give me a coursework solution, it worth 10% of your total exam marks. Okay, there will be just one coursework in this module. And then from part A, what's remaining is 35%. So 35% will be final examination. Everything will be from lecture notes. Don't go beyond lecture notes. If you fancy studying those books, please feel free to do so, no problem. But I will not ask you to give me an expression from those from the books. Everything is within your lecture notes. Okay. Plus, in second semester, since we have 2 labs of 5% each, we will have 40% from semester 2. So whatever you will study in semester 2 will constitute 40% of your final examination marks. Okay. So your final exam will look something like this. Part A, 3 questions. 1, 2, 3. For question 1 will have ABC, 2 will have ABC, 3 will have ABC. Okay. A and B will be from your lecture notes, concepts or derivation. C will be numerical. A, B will be question, C will be numerical. A, B question, C will be numerical. Okay? You will be asked to solve any 2 out of 3. Okay? So if you're not super comfortable with advanced electromagnetics, it's okay. You have a choice. If you're not super comfortable with antenna arrays, just cover 1 and 2. One will, you should cover 1 because it's fundamentals. Okay? So please give me an answer for question 1. Okay? So this is part A. Then you will have part B. You will have 2 questions, A and B, 1 and 2, and you will have to like solve everything. In part A, you have choice. In part B, you don't. So part A, you should pass. There's a system called moderation. So one will do the main thing, the second will cross check, moderate, and then they will discuss if there is some boundary cases. Okay. I will be checking part B. I'll be moderating part B. Stelios will be moderating part A. And there's a possibility we will have a third moderator if there is something that we want to discuss. Okay. So how was this module? Was it good? Was it difficult? Yeah. Too many equations? Too many variables? E, B, X, and Y, so on. Right. So a bit of advice: don't just close your lecture notes now. Go back home just once. Go through all lecture notes before December holidays. Go through all lecture notes. Fill in all the gaps. Okay. Only then put them in your store and just bring them out close to exam. That's what you will do practically. I'm not expecting you in semester 2 that you will be revising your notes. It's not going to happen. So just please have them filled. Be ready before your exams. Don't wait till last minute. Now things are fresh. There is a possibility that you will fill those gaps yourself if you have listened to everything. Okay. Plus, every lecture is being recorded. So if you have missed something, just go to that recording area. Just get that information out. Okay. The lecture notes were actually presented here in their complete format. Okay. So you have that possibility as well. Okay. So any questions? No. Okay. So there is a TEQ thingy, evaluation questionnaire, and MEQ thingy. So since I'm not going to be in here in next lecture, I would suggest, and I will keep chasing all of you till you fill in those TEQs and MEQs. Okay. So generally, response rate is down for everyone else, but for me, it's not because I chase everyone. So I will make sure that you solve that thingy. Okay. So please do solve that thingy. It will not take more than 2-3 minutes. It's just like click, 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 click. Okay. Okay. If you have any suggestion, feel free to send me an email. If you want to ask anything, email Teams. And thank you very much for attending these lectures, and I hope you all the best.